Okay. And what we I should give a little bit of historical insight into where these things came up. First, recall the Hamiltonian density. For we were looking at time independent configurations in the gauge. I guess A0 was equal to 0, and so we had something which looked like this. So I just need to fix factors of E squares and stuff like that. So okay, so it turns out that this similar thing appears even in superconductivity in something called the Landau-Ginzburg description. Of superconductivity. Okay. Yes. Okay. So the thing is that now superconductors are in 3 dimensions, while this problem we were looking at is in 2 plus 1 dimensions. So the way you sort of get to this thing is that you assume that things are independent of the 3rd direction. Okay. So what we think of, if you think of a vortex as something like a point in a plane, okay, then you can see that if you extrapolate it in a 3rd direction, it will look like a tube. Okay. So what we will call vortices in this context would end up being tubes, flux tubes. Okay. So so modulo that caveat, you will find that H gets replaced by the free energy. So you will end up with a similar setup out there, and so the question is, for instance, in type 2 superconductivity, you know that what happens is that if you turn on a magnetic field, it can, I mean, if it's completely, if you're below Tc, it would be superconducting. So there's obviously no way for flux to go through the thing, but really, I mean, if it is I mean, it can go through provided some regions become normal. Okay. So a cross section would look something like this. So you would have flux tubes going out here, and in this region the material will be non normal. Okay. And so this is a slice in 3 dimensions. So this would be like a tube which is coming out, and so these solutions in this model were actually constructed by Abrikosov, and so they are called Abrikosov vortices. And in fact, there are beautiful experiments where they actually show how these vortices actually will form a lattice. They could have interactions and stuff like that. So depending on what kind of thing they follow, I mean, people have really, I mean, experiments are really neat. I have not followed the literature, but you can search for it, and I'm sure you will get beautiful pictures of vortices. Okay. While so what so the extension of this, the realization that these two are the same, sort of goes back to Nielsen and Olesen, who embedded into a relativistic theory. So you could even think of this coming from a 3 plus 1 dimensional theory, where instead of thinking of the flux tubes, you think of them as strings. So they are sometimes called Nielsen-Olsen vortices or strings in 2 plus 1, or strings in 3 plus 1. Okay. And the finite energy condition, of course, in the other direction will get replaced to finite energy per unit length. So it becomes energy density in that extra dimension. So these are the small changes that you have to do, but from the viewpoint of solving equations, they are really the same. Okay. So let's get back to what we were doing. What we saw that we could rewrite this thing as a bunch of terms, and for now what I will do is I will not put lambda equal to any value. We will try to rewrite things like we did last time. And so let me look at that expression. The reason is that I claim that lambda should be equal to a square, but I think it should be equal to e square. So we will sort it out in a few moments. Okay. So the energy, So, for the rest of this discussion we will be back to 2 plus 1 dimensions with the obvious this thing. Okay. I think there would be a nice description of this in the Nobel side as well, because he won the Nobel Prize fairly recently. Okay. So, the energy was you need not note this because you already have this in your notebook probably. I need one more bracket, so let us use this bracket for that. Okay. So, you can see that that is just a rewrite of this term. So, it is really what is going on is that we should combine these two guys and try to make them work as one term. So, then we just write this as plus a half F12, okay. Pull out a half. So, it would be plus or minus root lambda by 2 okay. So, if I square this I will get F12 square half F12 square, which is this term, and if I square this I will get lambda square by 4 into 2, that will give you this term. So, but there is the cross term which we have to write, and so that would be minus or plus now actually it is a little bit more involved because I am wrong in saying that these terms only come from here, because there will be what happens is that let me write this and then you will understand what I am saying, and then so let me write this. So, that would be 2 times this. So, root lambda into F12 into phi 1 square plus phi 2 square minus a square. Good. Okay. So, the point here is that these two terms should actually be absorbed out here, and now this is where you have to, you can see that you will need to need this value to be something very special. Okay. So, that these two terms are already accounted for here, and as you can see there is really no a going around in this place. Okay. And so, this so the error now is very clear, lambda should be e square, not a square. Okay. So, I will just put that in. Okay. I will get root lambda out here, and I just erase this particular term from here, and then I get again plus or minus, this minus sign I absorb here. So, I get plus or minus e a square F12. Okay. Okay. And the energy which we worked out should be greater than or equal to 2 pi a square mod A. Okay, there was a divided by E, those things cancel out. Okay, good. So, now we have to get back to the equations. The equations correspond to setting these guys in the square bracket equal to 0. Okay. So, the first order BPS equations the first order BPS equations. So, we will consider the case when n is greater than 0, then I have done some redefinitions, and the other one would be okay. So, these are the the equations that you would get by, so these 2 plus these 3, the squares setting them equal to 0, that will let you saturate the bound. Okay. So, these are the these are the conditions. Or saturate rather, everything will satisfy the bound, but so I need to put in my definition. Z is just x1 or x plus iy, if I call x1 as x and x2, and I need a little bit more, dz bar should be equal to, that is a half, I think. Okay. The way to fix this half is that dz bar of z bar should be 1. Okay. And similarly az bar okay. I always like to work with a lowercase, lower index covariant, because that usually it goes with the derivative, and anything you make, any change of variables that you do the same thing for this, then your formulae look kind of nice. That is a natural thing to do. Okay. So, we need to solve these guys, and what are the boundary conditions, of course. So, limit as let us define rho tends to infinity of phi should be, mod phi should go to, it should go to its web, so that okay, it does not fix the this thing, and yeah. So, this is what we need to do. And so, now coming back to this, we can go ahead and see, we can simplify things. First thing we can see here is that this equation along with its complex conjugate equation lets you solve for az a in terms of phi. Okay. This should be equal to 0, I forgot to write that. So, for instance, this implies E az bar okay. I have just written 1 by phi, this thing as log of phi. Okay. This is what you get. So, and we can also, keeping in mind that this is what happens, we can put in an ansatz for a as some phi as a e power f of x or y, whatever, does not matter, of x and y, where f is some complex number. So, we can write f of x y I am just getting around to simplifying these equations, and another thing we know is that if n is greater than 0, one thing we know is that as you go around in the circle at infinity. So, one more thing we know is that at the circle at infinity, okay, when phi of, so rho is just plane polar coordinate. So, it is just, and let us say write theta as y inverse. Okay. So, phi of rho okay. So, one thing we saw is that the flux was nothing but the how phi the phase of phi changed, and so that should we can go back and write it in terms of the phase of phi, which is f2. So, okay, this is the definition that it carries that much, because that was the flux, right. So, this is what, so I have just translated that, because f2 is really the phase of phi, and this is what I get. Okay. So, this is the this is also another condition that we have to solve. okay, it is not enough to just say this. And so we just go ahead and so we have this, so we can work out what so this equation tells becomes another so this equation will so we this corresponds to well, let me repeat myself. A we have written in terms of phi, so now it is this equation which will give the equation of motion of which we need to solve. Okay. So let us simple algebra, which I will skip. So you can show that F12 with that thing is equal to oh, that is just a repeat of that equation. I am terribly sorry. Okay. So, but no, what we have to do is to write out what F12 is in terms of so we need to take a derivative of this expression. So you can see this already has one derivative. So you get a for this you have to take dz of this thing. Okay. So you end up seeing that you are getting the Laplacian acting on log phi. Okay. So what we get is the equation that we get is the following. So if you compute using that, you can show that E F12 is minus Laplacian of F2 or F2 or F1. Yeah. Okay. So if you plug these things in here, what you can see is that the equation of motion becomes minus so F12 would be this. This is what we get. So this is the equation that we need to solve, but surprisingly what we see is that there is no F2 in the problem. It looks like F2 is unfixed. Okay. The question is that a problem? Should we expect intuitively whether F2 should be fixed or not? So the equations, we have solved the equations now. So it says that this gives us F1, but it does not give you F2, but we do have some condition on this thing on F2, which is that, but that is an asymptotic condition, and while this says that we have to solve this equation. Any ideas? Exactly. So you should not expect F2 to be fixed, because you can always make a gauge transformation and make F2 look like something else. So what we did was to fix that gauge freedom by choosing a particular this thing. Okay. So it is really not it should be expected. So so really what we are getting is F1. Okay. So we need to go ahead and solve these equations, but we will not go ahead and solve these equations. I mean, there is some nice work by Taubes where he discusses the solutions to these equations, etc. But what one can show is by simple sort of mathematical arguments is to show that if I will only state these things, if the vortex number, okay, if the flux is, if there are n units of flux, then continuity conditions, then phi will necessarily have n zeros okay. These zeros need not be distinct, they can actually be coincident on top of each other, etc. Okay. And roughly what it says, so intuitively what it tells you is that what is happening when phi at a point where phi vanishes, you have full symmetry restoration. Okay. Or in the, if you go back to the superconductivity story where phi is the density of mod phi gives you the density of the Cooper pairs, it tells you that there are no Cooper pairs at phi equal to 0 when phi vanishes. So that is roughly where you would expect a normal state when there are no Cooper pairs. Okay. So these zeros can be identified with the locations, if you wish, of the vortices. In fact, you can also show that there's again this is a mathematical statement. You can ask how many, what is the moduli space of this solution. In other words, can I deform, what are the number of parameters. Remember when we went to the kink solution, we got something, we found that the location of the kink was a free parameter. Okay. We also saw that the velocity was, okay. These are, so you would say, so the location of the kink would be one parameter. So you can show that if you have n units of flux, the number of parameters that you, free parameters that you will have, you can make a count of it, it is called an index theorem computation, will be 2n, which is exactly in synchronization with this idea that you can identify it, like just tells you it is the freedom. So if I have a solution when I have two vortices, say located out here, I can keep I can move these things around such that I still have the same solution. Okay. So this is completely in synchronization with that picture that one has. Okay. So but what now the question is, what is the size of a vortex? But these vortices obviously it will be 0, but it won't. So what you will find is that you will, so let us say that this is a 0, you will find that it has a particular size, okay, and outside which to exponential accuracy or at phi equal to a, but inside this location in this region it would be deviating from a. Okay. So what is the size? Okay. And this actually, by the way, you can pose this question not necessarily for lambda equal to e square, you can pose it for any arbitrary value of lambda. And the thing is that, but there are what is the size, but we can now go back again to length scales in the problem. There are two length scales in the problem. Okay. Let us go back to the Higgs mechanism, there were two mass scales if you wish. One was m gamma, that was the photon mass, and the other was the eta, that is the radial direction, this thing. And so this was determined by the second derivative of the potential at the this thing. So this would be, this is let me just look up my numbers here. Yeah, m eta would be was lambda a by 2. Factors are important but not really, while the other one will be was E times a. Yeah, there is a dimensional problem. There is a square root out here. Yeah, now we are fine. Okay. So we have two length scales in the problem, and we can ask what these two would correspond to. But now, I mean, but again you can now again there is no need, we can look at the details of the solution, but we can see that the photon becoming massive, so that will have something to do with the magnetic field. So the size, so you can ask, there are two sizes in the problem. The first size is what is the size of the flux tube, okay, and that would be determined completely by this thing m gamma. In fact, you will find that the size of the flux tube will go, if you look far enough, will go like e power minus m gamma r. Okay, in natural units, remember m gamma is 1 by. While you can ask also, the other thing is, if you are looking in terms of Cooper pairs or whatever, you can ask how far where is the density of Cooper pairs really, what is the size scale associated with the Cooper pair density, okay, or that is the eta thing. So size okay, and that will go like e power minus m eta r. Okay, and this equality is roughly when these two length scales become the same. Okay, almost approximately you can see modulo this factor of 2, it looks like lambda equal to e square. Okay. So there are 2 length scales in this problem, and in fact if you go ahead and solve the other equation, which is the normal Euler-Lagrange equation, you will find that you will get naturally I mean you can linearize your equations. They are nonlinear equations, horrible to solve, but you can linearize, and then you will get Bessel functions, the k functions, with arguments which are exactly these. Okay. Initially I thought I would work out this thing in the class, but I think it's very tedious, but I will show you the idea of linearization of equations, because that is a very important trick. Okay. So we will so in your assignment you will work out the full Euler-Lagrange equation, and I will show you, I will write out that equation, and then I will show you how to simplify it. Okay. Okay. So now we are going to the general case. Okay. So lambda and E square are independent. Okay. So we need to put in some ansatz, etc., and I will do that in a moment. Yeah. So let us choose an ansatz. I will choose something for n equal to 1. Okay. So I am doing this for a single vortex. We can do it for more vortices, but so you can see that with this ansatz I have taken care of the fact that the binding number is 1. Okay. This is the simplest one you could write. Okay. If you wanted binding number 2, you could have put a 2 out here, and then I am assuming that it is I assume a radial ansatz, symmetric ansatz. So I put f of rho, that is just this function, and of course f of rho should vanish as rho goes to infinity, so that it becomes phi becomes a, mod phi becomes a. Similarly the vector field A, I assume that it has only a E phi component, and again you will see that this is kind of consistent with the flux being the suitable flux. This will give you what you need. So really what you have is f, 2 functions, 2 unknown functions, f of rho, g of rho. Unlike the other case, we had only one function phi, because everything was determined in terms of that. Now we no longer have that freedom. F and g are independent of each other, and so it's I mean slightly painful exercise to go through the fact that you are in plane polar coordinates, and so gradients and stuff like that will require you, I mean at least I need to write out the formulae correctly and work it out slowly. Okay. So for instance you can show that gradient of phi okay. So you get this piece because you are in polar coordinates, and f12 So now I will write out the Euler-Lagrange equations, and it will be horrible, nonlinear, f and g everything will mix with each other. So this is Euler-Lagrange equation for phi. You can see that it appears with 2 derivatives acting on f, but now the interactions take over. So you have a, you see you got a nonlinear piece g square, okay. So let us look at the nonlinear terms. We have this is nonlinear, in fact this everything here it's a little complicated because there is an f out here. So, f with anything will be gone. So, we just get rid of that. So, I will not underline things because it is too complicated to do it this way. This is one equation. The other equation So, of course, one of the exercises you have to do is to derive this, but another exercise is to ask how in the BPS limit, how is it that how do f and g get related, number one, and the other question is to ask whether given a solution of the BPS equation, does it solve this equation. You can ask these two questions and it should work, and it will. Okay. So, this is nonlinear. So, the way you linearize it is just basically throw away all the terms which involve which are nonlinear. Okay. So, let us look at this. This is g square, obviously nonlinear, throw it away. Okay. F square, this is also nonlinear. 2f, but 2f into 1 is okay, it is a linear piece, but 2f into f is again f square. So, that term is gone. So, now we look at this. So, there is only one term which is plus lambda a square okay, and the next equation is again, look here, this is g, this is linear, there is nothing in this part, but out here you can see there is g out here. So, this f is a nonlinear term, throw it out. So, you get e square a square g. Okay. So, now let us look at this in the linearized limit, and we can automatically see what is going on out there. We see both these things appear, these combinations appear. So, this looks, you see here we get this is m eta square and this is m gamma square, and what is happening out here, f is related with the phi part and g is related to this. So, it fits in beautifully with what we expect, and in fact these two equations are some things which you can solve, and you can solve for it easily. F of rho and g of rho go as. So, both of them are Bessel functions, and the asymptotic should be such that f and g should vanish. So, it is not the j for large values of argument it oscillates, while what you want is exponentially dying guys. Okay. So, that so the boundary conditions are imposed, are taken into account by which Bessel function that you choose. Okay. So, f0 goes like k of, I will just write it out. Okay. Now, you can see that these two length scales are equal when lambda equal to e square. These two length scales become equal, because k is this one, the 0 and 1 does not matter, the exponential part is still the same, they change prefactors, zeros, etc. change. So, you can see that this is really when these two length scales happen. Okay. And now we have to also check what is the region of validity of these things, and so the region of validity of this of the linear thing would be when f is closer to, f and g are close to 0. And so, now it is sort of like chicken and egg, you put it back and you say that this solution is valid at some distance away. Okay. Is that clear? But you can also go and ask, can I solve for the solution near a 0? Now, that would be a completely different problem, and then you have to take care of the full nonlinearity. Okay. But this is enough for you to tell you how the asymptotic behavior is. Okay. And another exercise would be to do it for not for for n vertices, etc. If you want, yeah, you just go ahead and do these things. Okay. So, are there any questions? So, I have about 14 minutes. So, in this 14 minutes I want to give you some ideas from topology, which actually are implicit in this thing, and we will look at it from the viewpoint of topology, and we will try to understand the vortex number. So, we got a topological current, but there is something more to this story. So, what did we see? We saw that the phase of phi, okay, changes by 2n pi, okay, when theta goes from theta plus 2 pi. Okay. So, the thing is the theta and the phase of phi are circle valued objects, in the sense that they are periodic. Are coordinates on a circle. That is just much more obvious. Okay. So, if you give me any phi, I can look at its phase at infinity and ask, and I get a map. So, any phi provides a map from S1 from one circle to another circle, and the first circle is theta, and which gets mapped to the phase of this thing. So, let us use last time what did we decide we will use for the phase of phi? Beta. Okay. So, this is a map where we write phi as some. Okay. So, you can ask, so suppose we are interested in maps which are continuous, smooth maps, that is all. Okay. We look at, so consider all smooth maps. Okay. Now, smooth here means just continuous, not even derivatives need not be there, it is just a smooth maps. So, let us call such a map, we will call it F. Okay. Where F is nothing but f of theta. So, we write this as beta equal to f of theta. Smooth maps from, okay. And the question is it possible to smoothly deform this is not the correct way to state it. Okay. So, we will define, okay. So, define an equivalence class as follows. Okay. So, suppose you are given two maps F1 and F2, we will say that they are equal, they are equal to they are related to each other if F2 can be smoothly deformed to F1. Okay. You can check that this is an equivalence relation. Okay. Now, the question is, what do we mean by smooth deformation? This is what we need to make it more concrete, and mathematically there is a way of doing this. So, what you do is roughly you look at you consider some so the way to do this is to suppose we have we define something called a bunch of maps f of gamma, where gamma takes values, gamma belongs to 0 and 1 to the interval, such that f of 0 is equal to f1 and f of no f of 0 should be f2 and f of 1 should be 1. Okay, and each of these for every value of gamma. So, in other words, you can this is what you mean mathematically precisely of making these two equal to each other. So, now the question which Poincaré asked was, can we actually, if you are looking at this simple example, can we actually specify what are all I mean, if you give me two maps, how do I know if this is true? If it is there, what classifies this thing? Okay. So, in this case the answer is very simple. Suppose you have a map with in this case it is just the winding number. So, if as theta goes from theta plus 2 pi, if it winds twice and there is some other map which is wound once, they will not they can never be smoothly mapped to each other. Okay. So, in this example the answer is straightforward, proving it is not, but the answer is straightforward. So, the answer for this answer is that two maps. So, this is if the this condition is they are called homotopically equivalent, that is a mathematical term, but from our viewpoint it just means that they are mapped to each other. Okay. So, the answer here we already know this is that two maps, okay, rather the equivalence classes are given by the winding number. Okay. By winding number I really mean how many times beta winds around when theta goes from 0 to 2 pi. Okay. And the reason to use this winding number thing is as follows. Any circle you can think consider the following thing. Suppose we have a rope, we have this thing and we take a rope and we wind it around certain number of times with orientation, of course. Negative means opposite, clockwise, anti-clockwise, looking upwards if you wish. And so, if something turns around twice and you not and then join the ends together, there is no way on earth you could change it from 2 windings to 1, for instance, unless you can sort of go out in the third dimension, which is not permitted, and unwrap it. Okay. That is not a smooth thing there. So really that is what is going on out here. So, but here actually in general you can consider smooth maps from S1 to any space, not necessarily S1. You can consider to any space, any manifold to be mathematical. Okay. And this so if you define the set of equivalence classes, you call them as pi 1 of M. These are looking at the set of equivalence classes from S1 to any space. So, a nice example, a second example would be take M to be S2, that is a sphere. Okay. So, you are asking so you draw a sphere. Okay. Now, the question is what I want to ask you is how many can you think of what would be the kind of equivalence classes you could have? Do we have any non-trivial winding which is possible? No, because anything can be shrunk. So, this whole picture here of which I drew in this formal thing can be also understood. I can keep shrinking these things, I can actually make it completely I can the only possibility is 0 winding, nothing. Okay. So, that is like saying pi 1 of S2 is trivial, there is only one kind of map, all maps are the same, all smooth maps of course are the same in this sense of same is given by this equivalence class. Okay. So, in some ways you can ask the questions about any manifold. So, this is actually kind of nice. Suppose you are kind of blind, if you have really thick glasses, and you cannot see properly, but you can actually quite I mean, so you want to distinguish between two things, whether one is a ball, and then there's another thing we could look at, like a torus. This has handles, and you can ask, what about here? Here in fact I can wind around something called an A cycle n times. I can also wind around another cycle 2 m times. Okay, so the blind guy can actually feel his way and see that this thing, you know, by just using this S1 as a probe, can see that can differentiate between a 2 sphere and this thing. Okay, in fact so in 3 dimensions, if M was a 3-dimensional space, then pi 1, the only manifold which has pi 1 of M, which is trivial, is the 3 sphere, and this was the Poincaré conjecture, which took many years to prove, almost 100 years. Yeah, so in 3, so here this M here could be any dimensional manifold. So you take M to be I guess there are some connected whatever 3-dimensional manifold, and if you are told that the pi 1 of that space is trivial, okay, actually you can extend this to any sense. Pi 1s of anything will be in S3 also, if for the same reason that you can shrink it, it's always trivial. Now the question is, are there any other 3-dimensional manifolds for which topologically speaking they have the same which has pi 1 which is trivial, and Poincaré conjectured that it was not true, that there was all these things should be equivalent to S3. That's one, I mean that's one part of the conjecture. Okay, so in some ways they are called topological because they don't need too much structure about the manifold, about the space, but they tell you a lot about these things. Obviously you can ask, can we generalize this further? Why should I look at pi 1? Why not look at S2, take sphere? So pi 2 of S, so you can define pi 2 of M. So again you look at maps from 2 sphere to any space, and with similar conditions. Okay. Again there is a nice thing, you pi 2 of S2 is Z again. Okay, and it's is there an easy way to see it? The answer is yes. You can reduce it to how you go to polar coordinates, spherical polar coordinates, and you can trivially write maps where the polar angle is winds around n times. So if you want a winding number 2 map of a sphere to itself, the way to do that is to think of a globe kind of thing, where you cut open a slit like this and you kind of drag it around once and do this back. That's an example of a map which has this thing, and you can see that is similar to the winding number thing for this thing. But in general you will, so you actually study pi n of M. So these are maps from Sn to N. So there is always one easy thing to remember, pi n of Sn is always Z, some kind of winding number. Pi 1 of torus is 2 Z's. Okay. There is some group structure associated with it, I am not getting into that. So this charge in fact has this whole topological structure associated with it. In fact all the charges have some kind of topological charges usually have some mathematical underpinning, and I just wanted to show you one example out here. Okay. So what I will do next is, in your next assignment you will have to work out the details of this particular solution, work out the Euler-Lagrange equation, verify for yourself that the BPS the first order equations is indeed a solution of the second order equation, fill in all the details. Okay. And so now we will move on to non-abelian gauge theories next, and we will also see how, before that we will spend some time looking at how symmetry breaking, how the Higgs how to look at symmetry breaking for non-abelian symmetries, continuous symmetries. We already know a little bit of Lie algebra now, so we know how to cleverly parameterize things, which means we can do the analog of the Higgs mechanism. We will see some interesting examples.